Okay, next up we're going to have Dr. Micha Manaucherhi, who is going to talk with us about drift management. Dr. Manaucherhi is a small grains weed science specialist at OSU and canola. I believe you've got canola in your assignment as well on that. And so she is going to visit with us about herbicide drift today. You've been here about a year? 8 months, closing in on a year. But we're fortunate to get her here in the program, and we appreciate you joining us today, Dr. Manaucherhi.
You guys hear me? Good? So, Dr. Bauman had some good jokes today. I don't like following good jokes. I'm a pretty serious person, so I'll just have to bank on this being a good presentation. Okay, well, it's good to be here. I did start at OSU on the main campus at the end of July, and my title is Small Grains and Canola Weed Specialist, but I was in Lubbock in West Texas, and I see some familiar West Texas faces here today, so that's nice. I'm working in cotton, so that's kind of why I'm here. I'm going to talk about off-target movement, specifically volatility and drift, physical drift. Okay, so just a quick outline so you know where we're headed, and this will probably be one of the shorter talks. Dr. Bauman did a good job talking about the technologies, our pros, some of our challenges. I'm not concerned with challenges. I think all tools have challenges, so the best thing we can do is get in a room and discuss them, which is why we're here today, so I think that's great. And Gary talked about labels. I missed that talk this morning, and I want to continue discussing benefits and challenges, specifically look at volatility and drift, and then wrap up with just a little bit of data. So, just to say again, I'm excited too that we have another tool to, one, manage some of our herbicide-resistant biotypes, but also to manage some of our just difficult to control weeds. I like Todd's slide on that not everything is about resistance. There are some other complications that we have to deal with as well. Protect our current tools. Dr. Bauman ended on that. And then at the end, what are we trying to do? We're trying to decrease our selection pressure for herbicide resistance, improve some of our rotation intervals to sensitive crops. Of course, these new technologies, like any technologies we have, are going to be the most beneficial when we use them as part of a system. And then you guys have heard about the new formulations. So, not a silver bullet, I'll tell you that again. There really are no silver bullets in my mind. Application timing is critical. I'm going to repeat a couple of things that Todd said. Yes, this isn't, we can't get away with controlling large weeds like we could with glyphosate, so just being really careful. I like that slide that he had on what we're losing when we make those later applications. I've done some timing work as well, and I would say 8 to 12 inches is where I really start to see a decrease in control. And then physical drift. So I want to start with herbicide fate. Let's all just go back and think, what happens when we make a herbicide application? There's actually a lot of things that can happen. So we have the plant. If it's a foliar application, of course we want plant uptake. If it's a soil application, we want to have contact, good soil contact, and then maybe some incorporation if it's mechanical, or incorporation by rain. But there's other things that can happen that aren't desirable. So volatility and drift will be the two that I'm going to focus on the next several slides. We can also have microbial degradation, which is usually the number one means that a herbicide breaks down in the soil. So from our microbes, we can have leaching and runoff, which we don't want. Adsorption with a D to our soil particles. And then, of course, every herbicide has a half-life, so it's going to break down over time. And then lastly, photo decomposition, so breakdown by the light. So what is volatility? We hear these words a lot when we're talking about these new technologies. It is the movement after application when a herbicide converts to a gas and moves off-site. What affects volatility? There's several things. One that's out of our hand is the formulation of that product, that vapor pressure. The higher the vapor pressure, the more volatile it's going to be, the quicker that it converts from that solid liquid state into a gas. Environment also plays a role. So when we have higher temperatures and low humidity, generally volatility increases. And for me, low humidity seems a little counterintuitive. I think I have a slide on this next. And then temperature inversions, which we'll go into some detail about. So why low relative humidity? Why do we see increased volatility when our relative humidity is low? So let's think about that plant in a foliar application. We all have heard of the term hardened off plants. Our herbicides, our foliar herbicides work best when our plants are actively growing and they're happy and healthy, and we can get absorption with the V into that plant cuticle. That's our number one barrier for a foliar herbicide application. When it's a dry day or our plant's stressed, that cuticle gets pretty thick and tough. And we also can get faster evaporation of that droplet that's on the leaf surface. Both of those things can result in decreased absorption. Temperature inversions. So I'm not a meteorologist, but we'll talk about temperature inversions in just kind of layman's terms. I'm sure you guys are familiar with them. During the day, we have radiation that's reaching the Earth's surface via short wave lengths. And as a result, we have energy from the Earth's surface being emitted back into the atmosphere via long wavelengths. So under normal conditions, when we don't have a temperature inversion, we say that the air is stable. And we have this gradual cooling into the atmosphere from that hot surface, and then it's getting colder and colder. When we have a temperature inversion, we have something that looks like this. We don't have stable air. We don't have that gradual cooling from hot to a little colder and then even colder. We generally have a warm layer of air that's trapped between two layers of air that are colder. And why does this happen? Basically happens when it happens is on calm, clear nights when we have really rapid cooling of the Earth's surface. And at higher elevations, the air isn't cooling as quickly, and so that's why we see those differences in air temperatures. So how do we know when there's a temperature inversion? What can we do? Well, on the science side, you could be measuring different elevations of the air. I don't have time to do that, and I know you guys don't because you're spraying a lot more land than I am. So there are some things that we can look for. I discussed that we sometimes see them on calm, cool nights. So when winds are really low, less than 3 miles per hour, we might just want to start being cognizant, okay, maybe there's a temperature inversion. They usually start at dusk and they break up into the early mornings. They can last a little bit longer. And when there is moisture in the air and we're having an inversion, you can see fog as a result. Okay, so you've heard about all of these products today. I'm going to talk about them a little bit more as they relate to physical drift. I missed Gary's talk, but I know he showed you guys the different buffer distances, and so I just want to go over that one more time. I need to hear things multiple times to kind of really get them in my mind. So before we look at some of the buffer zones, volatility, yes, I think we have heard today that these companies have done a great job on making these formulations less volatile. 96% less volatile for Endless Duo compared to traditional 2,4-D formulations. Same trend you're going to see with XtendiMax, a 90% reduction when we look at a formulation like Banvol, and an even further reduction from a formulation like Clarity. And again, the same trend with Ingenia, 70% lower volatility of our Ingenia product in relation to Banvol, and an increase or a decrease in volatility compared to Clarity. So we've done a pretty good job with volatility. What about physical drift? What is physical drift? So now we know what volatility is. Physical drift is just movement of that herbicide, and it's not on our target plant, it's ending up somewhere else, perhaps on a sensitive species. A lot of things can affect physical drift. In my mind, what's the most important is nozzle selection, or at least one of the pieces. Dr. Long is going to talk about nozzles next, and so I'm going to leave that piece out. He also has a fun spray table where we can look at some of these different nozzles. So what else? Our method of application. We're not going to be able to apply any of these products other than by ground, so we don't need to worry about movement via an aerial application. Boom height is important, which is why there are boom height restrictions on the labels, and we'll go over that just one more time. Wind speed and wind direction, that's also on all of the labels, and we'll recap that. We discussed air stability and temperature inversions, and air temperature and relative humidity. So I'll kind of keep this format for the products. Endless Duo on the left, XtendiMax, Ingenia, and Fexapan. For the dicamba-like formulations, you need to be 24 inches above your target pest or crop canopy, and for Endless Duo, you need to look at your nozzle manufacturer's recommendations. I'll also add, I don't know if Gary talked about this morning, I think this is critically important and has been a little bit of a challenge for me when I'm looking at the labels. When you go to your co-op or wherever you're going to buy this product, the supplemental label, to my knowledge, isn't going to be on the jug. And so it's really important that we make the extra effort, if it's not handed to you, that you go and look up that label. Wind speed for XtendiMax and Fexapan, 3 to 15 miles per hour. Ingenia, they have a note that if you are spraying less than 3 miles per hour, you better make sure that a temperature inversion is not present. And then Endless Duo, the maximum speed is 15 miles per hour. So I like that Dow has this picture on their label, so I've kind of tried to make it for the next, the other products we're discussing. We have the 30-foot buffer zone to a sensitive area, and we'll discuss what they are calling sensitive species. So I just mimicked this for the other products. For XtendiMax and Fexapan, depending on what rate you're using, if you're using the higher rate, it's 220 feet between your target crop and a sensitive species, and then 110 feet if you're using that lower rate. For Ingenia, it's 110. So you guys saw that, and I know that, but since we're talking about drift, I just wanted to recap that. What are sensitive crops? So most of them are going to say commercially grown tomatoes, other fruiting vegetables, cucurbits, and grapes. A couple of things to point out, that the Endless Duo label also says cotton without the Enlist trait, and that's just because cotton is that sensitive to 2,4-D. So that's critically important, that if your whole field isn't in 2,4-D tolerant cotton and you're spraying Enlist Duo, you still need to follow those buffer requirements. And then Ingenia, they have some extra crops, and I believe you have all of these on the handout. Okay, so let's say that we've done everything right and we still have some issues, whether they're related to volatility or physical drift. What's going to affect crop injury if we do have an incident like this? One is going to be your crop stage at time of drift, right? We have some crop stages that are going to be more sensitive to drift than others. Of course, your application rate, when you made that application, your crop distance from where that source of drift was, and then lastly, the environment. So who all has seen oxen injury? I think we all know what it looks like. Herbicide injury can be kind of difficult to diagnose in relation to other crop stresses that we have in the field. With oxens, it's usually pretty cut and dry. We see epinasty, curling and twisting of the plant parts, chlorosis, necrosis. Basically, oxens are attacking the meristematic regions of the plant, the growing point, and so we're going to see a lot of injury on those newer leaves that are being produced. 2,4-D versus dicamba injury. I think there's a lot of overlap between symptoms, but you will hear with dicamba you see more cupping, and with 2,4-D you see more strapping, where it looks like you just grabbed the end of the plant leaf and pulled it down. So that's kind of textbook. Again, I think you can see both of these symptoms with both of the products. Okay, so I'm going to wrap up with a little bit of data. I know no one really likes to see data, but there's not much. Looking at an endless duo tank contamination study done in West Texas, a 12-location belt-wide study looking at 2,4-D amine tank contamination and drift on cotton, so not using any of the new formulations. And then I'll wrap up with just a slide on soybean. I know this is more a cotton group, and I worked a little in soybean, so just to kind of show the relationship between the two crops. Okay, so what did we do in this study? We had 2 different growth stages of cotton, 9-leaf and first bloom, and we had different contamination rates. So we had, let's say you didn't rinse out your sprayer well, or you didn't rinse it out at all, and you had an 8% contamination decreasing by 10 all the way to a 0.0008% endless duo contamination. And so this is mixed with water still, as if you had finished spraying. What did we see? This is injury 4 weeks or 28 days after treatment. So on the y-axis we have percent injury. This is visual injury, so this is subjective and what I'm looking at in the field. And then we have our different tank contaminations on the x-axis. The yellow line, or the lighter line to you, is our 9-leaf timing, and the dark line is our first bloom timing. So I think what stands out most here was that our 9-leaf timing was more sensitive, and it wasn't until we got to about 0.80%, close to 1% of tank contamination, did we start to see some visual injury. Most people want to know, okay, so we have some visual injury, but how is that going to translate into yield loss? Is there going to be a yield loss? And that's why some of this work was done. And I can tell you that the take-home was visual injury and yield loss. That relationship is complicated. Sometimes you'll see injury that looks pretty bad and you won't see a yield loss. Sometimes you won't see much injury and it will translate into a yield loss. So no really take home on that relationship. So this is crop yield, and you can see it wasn't until the higher rates of contamination where we started to see decreases in yield. And again, that 9-leaf timing was more sensitive than first bloom. Okay, so I'll end with this drift and tank contamination study. This was a similar study, but it was done across the cotton belt. And we were looking at 2,4-D amine on cotton that of course is not tolerant to 2,4-D. And I'll just also point out, I should have prefaced this first, I'm talking about 2,4-D injury on cotton. We're in a cotton area, and I was living in a cotton area when I did this, but I could easily be talking about dicamba on soybean. So we had 12 locations. I'm not going to show any graphs just because there were so many different sites, but I'll just give you some of the results and discussion. In this study, we had 2 different rates of 2,4-diamine, about 1/400th, that was supposed to be our drift rate, and then about 1/20th, which we called our tank contamination rate. And instead of just 2 growth stages of cotton, we had 6, all the way from 4 leaf to 6 weeks after first bloom. So we were trying to find out, okay, at what time, where if we did have a drift incident or a tank contamination incident, would cotton be the most sensitive? And here was the take home. So when we had vegetative plants prior to reproduction, we typically saw the worst injury about 4 to 5 weeks after our application. For more mature cotton, it was about a week. Overall, across all of the sites, 9 leaf to 2 weeks after first bloom was the most sensitive to drift and tank contamination. So before and after reproduction. And then what I mentioned earlier, visual injury did not correlate well with yield loss. Couldn't find much of a relationship there. What about soybean? I haven't done any work on soybean with dicamba. There's quite a bit of literature out there. Seems that they're finding a better relationship between visual injury and yield loss, but I haven't seen any of that work. And then a similar trend in that around bloom is a very sensitive time if we do have off-target movement. So I'll end with the label is the law. You've probably heard that a couple times today. Just making sure that we're making the effort to look up these labels, especially if we're using them with new technology and we don't have that supplemental label in hand. On the university side, we're going to make all of the efforts we can to keep you informed with things like these quick spray sheets, but it's still not a replacement for the label, and it's still important that we are looking those up. Here is my contact information. I will be around for the rest of the day. If I haven't met you, please introduce yourself, and I'd be happy to answer any questions if you have them now or later.
When you were gathering data on yield loss, did you also get in on like crop and grade? Because I've had some fields that have been injured and they still were making a 3.5 bale, and they were a train wreck or something.
Yeah. We did do some quality work. So let's chat, and if you want to look at some of that, I'd be more than happy to share it with you.